explained about the basics of matrix completion based on decomposition. Let's explain what is what we have two different matrix. One of them is partial. For example, we have a matrix and we know some of the elements of this matrix, for example 1, 2, 3, 4, and we don't know some of them, and I put the question mark for that. The simple case of this matrix is, for example, you have a voting system, and for example some users, user 1 to user n, can vote for example movie 1 to movie, for example M, big M, and for example the number of users is very much and number of the movies again is too much, and no one for example spent all of his time or her time to, for example, rank all of the movies. Only the user ranks some of them and the rest is unknown, and we don't know what's the, for example, rank. And the rank here can be, for example, if you go to the, for example, some website, you can rank a movie by a number between 1 to 10. And this type of the matrix that is contain all of the user and all of the movies, and we have some unknown element on that. We call it partial because we don't have all of the matrix, and we can do some completion on this matrix, and for example estimate some of the number in this matrix and create a matrix that all of the elements is now. For example, if we have a matrix 1, 2, 3, 4, and this is some examples we can do. For example, 1, 2, 0, 0, and 0, 3, 4, 0, 1, 2, 3, 4, and this can be the completion of this matrix. And it's obvious that you can fill the different number to this matrix to make it a complete matrix, but here we are interested to add some information that doesn't, for example, change the information that we have really in the matrix. It's, for example, here the number of users is n, but the number of users that vote for one certain movie, it can be, for example, a small number k, and the k is very, very small, smaller than n. And here each user, for example, in average can vote for some movies that, for example, it can be P, and again P is very, very smaller than big N. And we find a complete matrix that all of the rows and columns are identical. It means we cannot do any exchanging between the column and add or subtract the columns, and for example create a column that all of the elements are 0, or we want to do completion that the result matrix is semi-positive definite. It means if I multiply the completion matrix to its inverse, the result it's always a matrix that the element in the diagonal is positive, and there is no 0 in the diagonal of the result matrix.
Excuse me, can you say again, what is K? K is the number of the...
here is the estimation of the average user that votes one movie. It is not related to this. It's only example that shows we have a lot of unknown number.
And how about the P and M? M is the column and P is the...
M is the maximum of the movies, for example, and N is the maximum of the user. And I want only saying that a lot of unknown elements are in the matrix, and we wanna extract a matrix that it has a low rank. It means the minimum number of the rows and columns that are identical. This is some introduction to, for example.
You shouldn't say identical, it's really dependent, right? Just say right. It doesn't have to be identical.
Yeah, it's true. Independent. I said, for example, add or subtract some of the columns cannot make a column totally zero. Might be.
So you mean the K is the number of the...
No, K is only example. K and P is only example to show, for example, there is a lot of unknown elements in the matrix. The number, I use the K to show, for example, K is very small, nothing else. Let's start with some definition and, for example, fix the notation. I said if we have an unknown element, we show it with question mark, and we define a finite size. Excuse me. If we have a finite size matrix M, that can be completed, we have a set S of M. It means there is some matrix M, which M bar is complete. Completion of M, and if M already is completed, the S of M.
Is it M bar is the matrix?
It's the different way of completion of matrix M.
Is it a matrix or is it a set?
It's a matrix. It's element of the matrix. For example, we have a big matrix M, not big. We have a matrix M, and we wanna complete it, and we can do it in a different way, and the result is a set that this completion can be from the original partial matrix M. And if originally was the complete, the set has only one element. And for example, if we have a two unknown, if we have a one question mark in the matrix, we have some way, for example, to based on how to fill this point, we have a different. We can have a different element in the S of M. And we define M R of M as minimum rank M bar, where M bar are in S of M. Minimum rank of a partial matrix M is the minimum rank of the one of the completion of the M, the minimum rank of the one of the completion matrix of M. Is it clear? And this minimum is available because the rank is, for example, a number between 1 to infinity, and we want to find a minimum, and always there is a minimum in the this set of the number start from 1 to infinity. And always, and we have, if we have m, it's equal to some submatrix A, B, C, D. Okay. There is a completion of the A belong to S of A, such that MR, minimum rank of M, is equal to minimum rank of A bar, B, C, D. Okay, because we can always we can do a completion on the submatrix and reduce the rank of that, and always we can do the completion of the submatrix, and the minimum rank of the total is equal to minimum of the original partial matrix. And there is some property here. For example, minimum rank of a matrix M is always smaller or equal than a rank of one of the way to complete this matrix. Also, minimum rank of M is smaller or equal to the if P is any okay, and if we concat two matrices A, B, the minimum rank of this matrix is smaller than or equal to minimum rank of A plus minimum rank of B. Also, the minimum rank of M is equal to minimum rank of M transpose. And minimum rank of a matrix A, B, C, is bigger or equal to minimum rank of A. Okay. This is some property that, for example, we can prove if you need any proof. It's possible. Let's keep the S of N is equal to conclusion.
Excuse me, the big A is the element?
It's a matrix.
No, the big A.
It's a matrix.
And you have, yeah, okay, cool.
Yeah.
Okay, it has a submatrix there?
Submatrix. Because it's not proof, but it's only explanation. For example, if you have a matrix and the rank of this one in the rest I will explain. If all of this matrix is the junk row, it's at least equal to the m, and it cannot be less than m, less than rank of a. At least you know this is the minimum rank of this, and because of this, if all of the rest of the matrix are contain the junk row or column, if the minimum is the rank of this submatrix, and the rest can be, for example, 0 or unknown. But this keeps the minimum rank of that at least equal to it. And we have a definition about the junk row and junk column. The definition said one row is junk row or junk column if it only contains 0 or unknown. And we can in the today or the next session you can see we can, for example, delete the row that is totally 0 or totally unknown from the matrix to reduce the size of the matrix. And let's add here the, for example, minimum rank of the j is equal to 0 if j is the junk row okay. And there is a theorem that said if we have a matrix M which is equal to, for example, some junk column and one matrix N, the rank of minimum rank of M is equal to minimum rank of N, because the because we know the here we know the minimum rank of the A is less than equal minimum rank of the sub matrix.
What's it, junk row?
Sorry, junk row. Yeah, junk row or junk column is the, for example, something like this, all 0 or all it's the combination of 0 and unknown elements.
This I have a junk.
Yeah,
Junk.
this element is junk. It can be this or transpose of that.
I know now.
This is the column, and maybe we can have the row, junk row, because there is no, for example, information in this. This is a 0. It means, for example, no rate, and unknown. For example, again, unknown. And we define the rank of the junk row is equal to 0. And we know if we have a, for example, one column and one matrix, the result is the less than the rank of, for example, the junk and the original N. And this one is equal to 0, and the rank of this must be less than rank of N. And also we have, for example, here, if we have, from here we have, let me write it down. From here we have M, J, N. minimum rank of Jn is less than equal to minimum rank of the J plus minimum rank of N. Yes, and this one is 0 because it's less than equal to minimum rank of N. And from here we have minimum rank of let's, for example, A is equal to J and B is equal to N and the rest is 0, and it's, for example, J again N, and here we have this bigger than equal to the one of the submetrics has its minimum N, and these two it says is less than minimum rank of N, and here is the bigger than, it must be equal to the rank of the matrix without the jump column. And again we have here that said the transpose of the minimum rank of transpose is equal to the minimum of the rank of origin. Because of this, it's the same of the column and the row. Okay, and it also can be for the, for example, Jn for one junk row or junk column. There is a definition that said two metrics M and N are equivalent. It means we can do column or row exchanging. It means if we have a big matrix, we can, for example, change the location of one row and with one column with another column and one row with another row, and make these two matrices as the location of the unknown are in the same location, and the rest of element are the same. These two metrics are equivalent, and the minimum rank of the M is equal to minimum rank of
J and J M. I mean, you have just instead of the one, yeah.
And JM.
Yeah.
Okay.
How we can find the?
Yeah, it's same as this one. You
Is
can.
the NM?
Yeah, NM. Yeah. The exchanging the row and column let you to, for example, move this here.
Is that NM?
Yeah, and again you have, for example, here two junk column, and you can ignore this two because they didn't change the rank.
And also, if you have the row, junk row and column row,
Yeah,
both
you
of
can.
them,
Yeah, you can do, for example.
it doesn't matter. You just
Yeah,
remove
for
the
example,
junk.
you have N, J, and
JM, for example.
no. You have one column and one row. Okay, you can first, for example, delete this one and again delete this one.
And
In the second one, you have only, for example, a half row,
yeah.
and the result again is N. And there is a definition for unknown diagonalization. It says, for example, U of diag B1, B2 to Bn defined as matrix B1, B2, Bn, that the rest of
Excuse me. For the previous question, has the NN, you have NN,
Okay.
so the rank of the NN
the minimum rank of
is,
the matrix
Zero,
N
yeah,
is equal to minimum rank of N. Okay?
why?
Because you have the same
same column,
column here
yeah,
and
column.
some same one, and you can delete
Same
one
row.
of them.
Yeah.
You can subtract one of them and create one
Yeah,
junk
exactly.
and delete it, and do for all of the rows, and the result is on the end.
Okay, just you mean that just remove one of them.
Yeah, row by row or column by column. But in this case, you cannot do in the column by column.
Yeah.
It must be the row by row. But in the, for example, in the big matrix, you do, for example, a one term, try to find two same, for example, column, remove that, and again start for example, rows. Find one row and try to remove it, and again column, row. It's back and forth to make the matrix as small as possible. Okay. The matrix M is unknown diagonalizable if M is equivalent to the unknown diagonalization of, for example, matrix A and B, where at least one of A and B has a zero or unknown entry. Excuse me, has one non-zero and unknown and known entry. Okay. Okay. A and B at least must have one element that is not zero and unknown. It means A and B is not totally junk. And I think this and this, and let's try this. And there is a theorem that says if M is equivalent to unknown diag of to N matrix B1 to Bn, the minimum rank of M is equal to maximum of minimum rank of each element in this matrix. I is between 1 to N. Okay? And there is a proof for that. Let me write it down, some number here to, for example, this one is 5, 6, 7, 8, 9, and something that I mentioned about the row exchanging, if we can do, for example, row exchanging and create a m equal to n, the minimum rank of m is equal to minimum rank of m. I write it here. For the proof of this one, we can show, for example, if we have an m, it's on the out of A and B, where the minimum rank of A is a small a and minimum rank of B is equal to a small b. By number 9 here, because this one is A, B. Okay. By number 9, we know the minimum rank of M is bigger, equal to maximum of A or B. Okay, because this matrix is bigger than the minimum rank of each element, and for example, if the minimum rank of this one is A and for example this one is D, the A is bigger than the biggest one in these two elements, and the maximum of AB is the maximum rank of this submatrix, and the original matrix M, the rank of that must be if we do the completion, on the B and A, and we have A bar and B bar as a complete matrix of A and B, and the rank of A bar is equal to A, and if we do the completion, the rank of A bar is equal to A and rank of B bar is equal to B. This is true because we defined that the minimum rank of a matrix is the rank of the completed matrix of the incomplete matrix. And by number 6, we have, if we have any partial completion of a matrix, the rank of the partial completion is more than the original. Based on this, we have the minimum rank of M is less than minimum rank of on the of A bar, B bar. Because this matrix is not completed fully, because there's some unknown still, but we do only the completion on the sub-matrices, matrices, and the rank of this one is bigger than this because it's the minimum possible rank of the M. And we have this one and this one, and based on these two, we know the minimum rank of M is between minimum rank of this one from this part, and this is from here, and we mix these two, and we know the minimum rank must be more than maximum of each element, and is less than rank of the completion of each submatrices. By changing the row and column, we can have the, for example, first A row of completed matrix A bar as a first A column column of A bar is equal to, for example, roll of A bar, and first B column of B bar is equal to code of B bar. And now, for example, if we assume the for this case, we assume the A is less than or equal to B. By this assumption, we can complete the matrix on diag of AB by filling something like this. For example, A, I, can be completed as, for example, A, I bar, BI, and if I is between 1 to B, the result of this one AI bar, BI bar, and if the I is between B plus 1 to A, the combination of AI and for I that is bigger than I, we make use of the fact that I is a linear combination of all of the columns that this column are less than R, A. And for example, we can fill the AI bar unknown with the AI bar and sigma k equal to 1 to n of AIK BK bar when I is less than I, and similarly for the B, we can do BI with sigma k equal to 1 to A, sorry, 1 to B, and BIK, AK, and BI bar.
why I get how to just fill unknown with the sigma there.
Okay, there is some unknown, and we can fill it with this. This is the combination of the these rows. For example, we have okay, here the AI is the linear combination of the k column of the original matrix, because we use only the first A matrix and use that. And we know that the, for example, first A column are used here to used as a for the complete the unknown values. We assume that, for example, only use the A first column and B first column of the A and B where they are the complete, and we call them as A and B as the minimum rank of the A, because we know that in the completed matrix we don't have any columns that the combination of that can create another column. In the completed matrix, all of the column is unique compared to the other columns. And in the not completed, you have some columns or some rows that you can, for example, delete it or make it a jump column by add or subtract some column of the completed matrix. Okay, because of that, the rest column of the uncompleted matrix can be the combination of the sum column of the complete matrix. I think I lost the track. Close to the start about the, for example, decomposition. Let's explain it for the. I explain it again. Why the sigma of this one? It can be the summation of the element of the completed matrix, and rest it's the iterative algorithm for using this fact to decompose a bit matrix and complete each small matrix and apply the reverse process to complete the big matrix.